A study of the learnability of relational properties. This paper introduces the MCML framework for quantifying the learnability of decision trees with respect to entire state space. The performance of ML models is normally evaluated on test datasets. However, discrepancies between samples in test datasets and samples in entire state space can lead to a false confidence in the performance of ML models. MCML uses differences between the ground truth formulas written in Alloy and CNF formulas generated using translation of decision trees to quantify the number of samples in entire state space on which the decision tree will predict a wrong label. We introduce the idea of quantifying differences between two trained decision tree models, and we also conduct a systematic study of learning 16 relational properties using 6 ML models. Results show that simple ML models can achieve high performance when evaluated in common setting of train and test datasets. However, MCML metrics show that the performance can degrade substantially when tested against the entire state space. This shows the usefulness of model counting for quantifying the true performance of ML models. Relational properties have a vital role in testing and verification of software systems. These properties can be written as test assertions to enable assertion-based checking techniques. These properties also enable deep semantic checking and are helpful in error recovery and repair. These properties are manually written, which can make them error-prone. This can lead to false alarms or the bugs can go undetected. We believe that machine learning can be used to help learn these properties. Therefore, we conducted a systematic study to see the learnability of these relational properties. For each property, we wrote ground truth formulas in Alloy. We then enumerate datasets that include samples satisfying a relational property as well as samples which violate the property. We then train decision trees on those datasets and evaluate the performance of decision trees on test datasets. We then employ MCML framework to translate a decision tree to a CNF formula. Once we have the ground truth formula from Alloy and translated CNF formula from decision trees, we can quantify the learnability of decision trees with respect to entire state space using the semantic differences between the two formulas. In summary, there are three main contributions for this paper. The first contribution is learning relational properties. We present a systematic study of learning 16 relational properties using 6 off-the-shelf machine learning models. The second contribution is the use of model counting to quantify the performance with respect to entire state space. We reduce the problem of evaluating the performance of trained decision tree models over the entire input space to the problem of model counting and employ cutting-edge approximate and exact counters to embody the deduction. The third contribution is the use of model counting to quantify semantic differences between trained decision trees over the entire input space without the need for ground truth formulas or evaluation datasets. The figure shows an Alloy specification that declares a set S of atoms, a binary relation R, and 4 predicates that specify reflexive, symmetry, transitive, and equivalence relations. The command run equivalence for exactly 20S instructs the Alloy analyzer to solve the formula that define equivalence relation with respect to a scope, that is, a bound of exactly 20 atoms in set S. The analyzer uses the bound to translate the Alloy specification to a propositional satisfiability formula and uses off-the-shelf SAT solvers to solve it. The Alloy analyzer supports incremental solvers that can enumerate all solutions. State space grows as the number of vertices increases. For example, for just 7 vertices, the state space has size 2 power 49. Alloy analyzer translates this problem to a CNF formula that has around 19,000 variables and 27,000 clauses. We use 2 model counters for our work, namely AccMC and ProGMC. AccMC reports an approximate model count of 11,264 in just 18 seconds. ProGMC reports the exact model count of 10,946 in 351 seconds. The count reported by ProGMC is, as expected, the exact number of solutions we get using the Alloy analyzer. The figure shows a decision tree with 2 inputs, X and Y, and 4 paths. Path condition for label 0 is disjunction of each path that lead to label 0, and path condition for label 1 is disjunction of each path that lead to label 1. For example, path condition for label 0 is X and not Y, or not X and Y. Similarly, path condition for label 1 is X and Y, or not X and not Y. Negating the path condition formula for label 4 gives us the path condition formula in CNF form for label 2. Negating the path condition formula for label true gives us the path condition formula in CNF for label false. Our translation creates a compact formula directly in CNF without introducing any auxiliary variables. For a decision tree with n leaf nodes, the number of path conditions is n, that is linear in the tree size. Let phi be the ground truth. Model count of the formula created using conjunction of ground truth formula and path condition for label 1 gives the count of true positives. Model count of the formula created using conjunction of negation of ground truth formula and path condition for label 1 gives the count of false positives. Model count of the formula created using conjunction of the negation of ground truth formula and path condition for label 0 gives the count of true negatives. Model count of the formula created using conjunction of ground truth formula and path condition for label 0 gives the count of false negatives. Using these four counts, we can quantify accuracy, precision, recall, and F1 score with respect to entire input space. Quantifying the differences between decision trees follows a similar procedure as outlined earlier. However, instead of doing conjunction between ground truth formula and path conditions, we do conjunction between path conditions of two decision trees. The semantic difference diff in D1 and D2 is quantified as the ratio of the number of inputs x such that decisions for x differ between D1 and D2 to the total number of inputs. Similarly, in D1 and D2 is quantified as the ratio of the number of inputs x such that predicted labels for x match between D1 and D2 to the total number of inputs. For the study part, we use 16 relational properties and 6 off-the-shelf ML models. For quantifying the performance with respect to entire state space and differences between two trained ML models, we focus on decision trees. For each property and scope, we use alloy to create two sets of solutions, positive solutions and negative solutions. For positive solutions, we use the set of all solutions enumerated by alloy's back-end SAT engine with respect to that scope. The number of negative solutions is much larger than the set of positive solutions. Enumerating all negative solutions is infeasible. Therefore, for negative solutions, we sample them at random from the entire state space. We create a candidate solution at random and then confirm that it does not satisfy the property using the alloy evaluator. Each data sample has a feature vector and a binary label. There is 1 for the positive class and 0 for the negative class. We study each property under two settings for symmetry breaking. In first setting, alloy's default symmetry breaking constraints are used. In second setting, no symmetry breaking constraints are added by the alloy analyzer. We also evaluated our experiments using 5 different train test ratios, specifically 75-25, 50-50, 25-75, 10-90, and 1-99. This is to evaluate a wide range of settings. We use 4 metrics to report the results of the classifications. These include precision, recall, accuracy, and F1 score. The first research question is how effective are ML models in learning relational properties. Dataset was generated using default alloy symmetry breaking. The dataset is further split into training and test datasets using the different ratios mentioned before. All models exhibit high accuracy and F1 score. The range is from 0.94 to 1. Overall, all models achieve good performance, and surprisingly, even for a small train test ratio, 199, models achieve good performance. The second research question is how well do decision tree models generalize outside of the test set? To evaluate in respect to the entire input space, we use ground truth formulas constrained with symmetry breaking conditions. When decision trees are evaluated on the test set, performance metrics are around 0.99. However, when decision trees are evaluated on ground truth, precision and F1 score decreases to 0. In fact, the precision is around 0 on 12 properties. This shows that models are biased towards classifying an example as positive, likely learning patterns present in training dataset but not generalizable. Previous section showed encouraging results of learnability of relational properties, but evaluation in respect to entire input space shows concerning issues if models are to be used in the wild. With respect to time, MCML reported results for 12 properties within 10 seconds and 3 properties within 220 seconds. The third research question is how do symmetries in the dataset affect performance of ML models? Here we perform similar experiments as we did in research question 1, except that symmetry breaking constraints were not used. This means that our datasets now have symmetrical instances. Results show a noticeable decrease in terms of accuracy and F1 score introduced by symmetries. Results show a similar trend as before, even when enhancing the training set with symmetric examples doesn't allow the decision trees to generalize. The fourth research question is, how does mismatch in symmetries present in the training and evaluation sets affect the performance? There were two cases. Symmetries are not present in the training set but are in the evaluation set. Here, when decision trees were evaluated on the test set, performance metrics were around 0.99. However, when decision trees are evaluated on ground truth, precision and recall and F1 score decreases to 0. Results show that decision trees perform worse when they are trained on dataset without symmetries and evaluated with respect to entire state space with symmetrical instances. This result is expected since the trained model did not see any symmetrical instances in the training dataset and is likely to perform incorrectly when tested on permutations of the same instances on evaluation set. When symmetries are present in the training set but are not in the evaluation set. When decision trees are evaluated on test set, performance metrics are around 0.99. However, when decision trees are evaluated on ground truth, minimum precision and F1 score decreases to 0 on most cases. This shows that even when training set is richer, that is, it contains symmetrical instances, even then decision tree models still fail to generalize in respect to entire input space. The next research question is about the quantitative difference between two decision tree models. Here, we train two decision tree models for each property using different values of hyperparameters and measure the difference between the two. Difference column shows the percentage of cases in which the two models make a different prediction. In all cases, the difference is small. MCML is able to quantify that the models represent the same property, that is, the difference scores between the two models in respect to entire input space is low. This makes MCML a powerful technique for evaluation of models. One can take a smaller compressed model and rigorously quantify it in respect to a larger model to see if it can be used as a replacement. MCML is able to detect this for 12 properties within 10 seconds and is able to detect all properties within 1000 seconds. MCML allows quantifying model generalizability even if the training distribution is different from the true distribution. Table shows the results of decision tree trained using different valid and invalid ratios. The traditional metric reports precision to be around 0.97 for all ratios, whereas MCML metrics report that the precision is as low as 0.19 and is 0.97 only when the models are trained on datasets having a class ratio of 199, which is very close to the true distribution with respect to entire input space. Traditional metrics fail to capture the performance for almost all class ratios. In contrast, MCML metrics allow precise quantification of true performance of the trained model for each class ratio. Use of alloy introduces a potential for bias in the results due to specific techniques employed by alloy. When symmetry breaking is turned off, propositional formula alloy creates faithfully represents the original property. Set of solutions at the alloy level is the same as the set of solutions at the propositional level. For positive data samples, we use every solution enumerated by the set backend. Any set solver that enumerates every solution will create the same set of solutions. Indeed, different solvers may create that set in a different order. However, our experiments do not depend on the order in which the solutions are created. For negative data samples, we do not use any constraint solving at all, and instead select a set of negative solutions at random. When symmetry breaking is turned on, alloy adds symmetry breaking predicates to the propositional formula before it is solved by the backend SAT engine. This enables faster solving by helping SAT prove more effectively. The results are specific to the symmetry breaking predicates added by the alloy's default symmetry for each property and score. A different setting in alloy or a different tool may lead to a different result. We plan to extensively study effects of symmetry breaking in future work. To our knowledge, our paper is the first empirical study of learnability of relational properties with respect to entire input spaces. Two recent projects use a variety of ML models to show the learnability of properties of code, specifically dynamic data structures in Java programs. Both these projects used traditional metrics with training and test datasets and did not evaluate the performance of the trained models with respect to entire input spaces. Spec learning framework and VC theory enable formal analytical characterization of the number of examples needed to train models for binary classification tasks. The PAC learnability concepts provide limited insight in the performance of methods for learning relational properties. This is because for relational properties, number of positively labeled samples in the domain set is often orders of magnitude smaller than the number of negatively labeled ones. Precision, recall, and F1 score are more informative performance metrics than the average 0-1 loss. The latter is the focus of the PAC learnability analysis. MCML can precisely quantify generalizability both in terms of the accuracy as well as precision, recall, and F1 score with respect to a given ground truth. MCML complements existing theoretical frameworks by providing insights based on empirical evidence from controlled experiments using various relational properties that are common in software systems. This work introduced MCML approach for empirically studying the learnability of relational properties. MCML quantifies the performance of and symmetric differences among trained ML models, specifically decision trees, with respect to entire input spaces. The results show that relatively simple ML models can achieve surprisingly high performance when evaluated in the common setting of using training and test datasets. Use of MCML metrics show that the performance can degrade substantially when tested against the entire input space, indicating the high complexity of precisely learning these properties and the usefulness of model counting in quantifying the true performance. MCML offers exciting new directions for leveraging model counting in machine learning. It provides quantitative answers to key questions like, did we train enough? How much did we overfit? And is this model basically the same as this other model? And it also allows informed decision making for ML-based systems. For example, should a deployed model be replaced with another newer model? Thank you.